Hola, buenas tardes, bienvenidos, bienvenidas a otro coloquio del CIMA de Cabo. Hoy tenemos...
Hola, buenas tardes.
Uy, me puse el YouTube. Hoy tenemos el gusto de tener como oradora a Marcia Zilli. Marcia es una ingeniera ambiental, hizo un máster en recursos hídricos e ingeniería ambiental en la Universidad Federal del Paraná en Brasil, y realizó su doctorado en geografía en la Universidad de California, Santa Bárbara. Se graduó en 2017 y después de terminar su doctorado, trabajó como investigadora en el INPE de Brasil, el National Institute of Space Research, estudiando impactos del cambio climático en la agricultura brasileña, y desde 2019 realiza un postdoc como investigadora visitante en la Facultad de Geografía y Ambiente de la Universidad de Oxford. Bueno, muchas gracias, Marcia, por aceptar dar esta charla, y si querés empezar a compartir tu pantalla, los dejo con vos.
Buenas tardes. Gracias por el convite. Perdón, no hablo bien español. Voy a cambiar a inglés ahora. So good afternoon, everybody. Thanks, Julia and the committee for inviting me for this talk. It's really nice to be able to speak to you guys here at the University of Buenos Aires. I will share my screen now. Since I am basically an undergrad student, I've been studying the South Atlantic conversion zone and different synoptic features that causes precipitation over South America, especially during the summer. And my most recent piece of work is what I've been developing here in Oxford, together with Neil Hart, which is my supervisor, my PI here in the research that I'm working. And also, to develop these results that I'll be presenting today, we have a partnership with different researchers on the Met Office, also here in the United Kingdom, and in the National Institute of Space Research in Brazil. So I would like also to acknowledge them for their contribution on this research. So basically, I'm going to talk about the use of synoptic cloud band events in the analysis and identification of biases in climate simulation. So let's start first with what is a cloud band event. There we go. So as I mentioned before, I spent most of my career studying the South Atlantic conversion zone, and this is a good example of a cloud band event, a tropical cloud band event that occurs over South America. So in a more formal way to say, this cloud bands, they are areas of continuous low outgoing long wave radiation, OLR, that connect convective areas in the tropics with extratropics, and they are responsible for the largest fraction of precipitation over the rainy season in the areas where they occur. And they are usually related to floods and landslides when they are very intense or when the season is especially active. But they are also related to dry spells and droughts if you have a characteristically inactive season. This map on the right is showing the location of this main cloud band. So over South America, we have one of the examples of a cloud band would be the South Atlantic conversion zone. Over Southern Africa, we have the South Indian conversion zone. Over Pacific, we have the South Pacific conversion zone. And over Australia, we have the Northwestern cloud band. So one thing that I want to highlight here before I start digging a little bit more into this is that this cloud bands, they are one example of a cloud band is the South Atlantic conversion zone, but we can have other weather systems forming this. So I'm not looking only at those events that last more than 4 days, as is the definition of South Atlantic conversion zones, but at everything that connects basically the Amazon with the subtropical South Atlantic Ocean over Brazil, over South America. So it could be even like a cold front or something like that. So the methodology, this already brings us to the methodology. We use an algorithm that was first developed by Neil Hart to understand the South Indian conversion zone over Southern Africa. And I adapted this algorithm to South America. and it identifies features, objects, or areas with OLR below a certain threshold, and aggregate this into events. So the figure on the right is showing an example of one cloud band, which is highlighted with the contour in brown. And to be classified as a cloud band, as I mentioned before, it has to extend from the tropics to the extratropics in this kind of diagonal fashion, and be, of course, with OLR below a certain threshold. This red rectangle here is the study area for this specific results that I'm going to show in the beginning of this presentation. And the other lines here doesn't matter now. So to identify this cloud band, first, I use outgoing long wave radiation from NOAA dataset. It has a daily data set with a 1 degree resolution. Then to characterize this cloud band, I use ERA 5, so precipitation from ERA 5, and also the winds from ERA 5. In terms of precipitation, we also analyzed different data sets as stream, and also observed a data set available for Brazil, and we found very similar results. So ERA 5, since ERA 5 has this longer time series with a kind of similar quality as observations, we decided to keep it with ERA 5. So this way you can have results for the entire South America. And besides being like a tool or framework to identify these events and also identify the circulation that is causing these events, this framework can also be useful to understand biases in climate models. So for that, I'm going to show some results using global climate models. So the one on the left, BAM, is the atmospheric only climate model from the National Institute of Space Research in Brazil. And I'm also using 2 different resolutions of the Hadley Center or the Met Office global climate model, both either in the AMIP version, so the atmospheric only version, or also the CMIP run for the historical scenario. And more recently, I've been also trying to develop this and analyze these results using convective permitting models. So for that, I'm going to show a few results from the Met Office convective permitting model. So just to keep in mind, we have 2 versions. One is the control version, which is forced, or where the convective permitting model boundaries is forced by the global climate model in the higher resolution that they have in the Met Office. So it's a resolution higher than this, the N216. This N512 will have a spatial resolution of about 0.25 degrees. So this is the control run. And there's also another run, which is called the hindcast run, where the convective permitting model is forced by ERA entering data, downscale to 25 kilometers using a regional climate model, and then used as an input for the convective permitting model. So I will start with the results for the observation. So outgoing long wave radiation and precipitation from ERA 5. So this first graphic, this first slide is showing kind of a summary of what we see during the summer season in South America. So the map on the left is showing the number of days during the rainy season, so November through March. Both maps, sorry, showing the number of days. So I will start with the climatology on the top, with the seasonal cycle. So these cloud bands, they tend to occur more frequently during the summer months. And here, just to kind of like for clarity, I divided them according to their duration. So I separated all events that lasted more than 4 consecutive days, and I'm going to call this persistent events. And then all events that lasted between 1 and 3 days will be called transient events. So most of the time, these transient events are maybe formed, for example, for like it would be kind of like a cold front or something like that, and they can occur even in the winter. While the persistent events, they are more similar to the circulation during the persistent events are more similar to what we would expect from a South Atlantic conversion zone over southeastern and eastern Brazil, and they occur mainly during the rainy season. So the map on the bottom, the contour is showing the total precipitation during these events over the rainy season. So for example, the persistent events, we see that the core of the precipitation is located over eastern Brazil and southeastern South Atlantic, southwestern South Atlantic, sorry. And the shades is showing their contribution, the contribution of these events to the total climatology. And we see that over this region, these events can contribute to about 60% of the total precipitation during this month. If you look what happens during transient events, they also kind of like occur over a little bit to the south. So they can reach a little bit like central Brazil and some parts of southeastern South America. But they are very important to precipitation over this region, over southeastern South America. So this image shows more or less kind of like what happens when we have the active dipole of the South Atlantic conversion zone and the inactive dipole. So like when you have the South Atlantic conversion zone more over tropics or more over the extratropics. Okay. So as I mentioned before, this framework allows us to identify events throughout the time series. And we can actually visualize these events using this webpage. This webpage was put together in partnership with the Institute for Earth Analysis. Sorry, I forgot the actual acronym of IEA. It's an institute from Reading, near the University of Reading in the UK. And they put together this website, like the visuals of this website using this data set that we developed. So on this website, you can see things like for example, this is the landing page where you see the spatial signature of this cloud band, the climatology. So this is the number of days with events throughout all the years of the analysis. And navigating on this webpage, you can actually check each one of these events that we separated in each one of these states with events. So this is an example of January 1st, 2010, where we had a cloud band identified here by the contour over São Paulo and Rio de Janeiro, so southeastern Brazil. The shades are indicating the total precipitation during this event. So quite intense nuclei here over southeastern Brazil and South Atlantic Ocean. And the QR code is covering the caption, sorry. And also we can see where we had natural disasters related to this cloud band. This natural disaster database is limited to the southeastern Brazil, but it's kind of like interesting to see the importance of these events throughout the years, for example. So if you are interested, you can check this webpage on the QR code on the right, and I will show it again at the end of the presentation. So as I mentioned before, we can use this to identify the main circulation features related to this event. So most of the time, we know that this cloud bands in general, they form, or the South Atlantic conversion zone in particular, they form when we have disturbances from the extratropics going into the tropics, represented here by the red line, and also intense convection over the Amazon, providing the moisture, mainly the moisture that will feed this cloud band event. So we have the extratropical forcing as the Rossby wave propagation. We have tropical forcing, so the diabatic heating from the Amazon, for example. And we also can have local forcing in terms of land atmosphere interactions, especially related to land use change and other regional influences. So how does this translate into the currents of this cloud band? So again, I'm dividing this into persistent events and transient events. So for those events persisting more than 4 days, when we look at the climatology, so not just looking at these events, but like the basic state of the environment during this event, we see that in general, we have mostly easterlies over tropical Brazil and westerlies to the south, and the subtropical jet is located a little bit more to the north. So just to compare with the transit events, during transit events, this area of easterlies are shifted a little bit to the south, so the Rossby waves cannot propagate too much into the tropics. So basically, we need the subtropical jet and the westerly winds to allow for the propagation of this cloud band, or sorry, the propagation of this Rossby wave, so that it reaches this subtropical / tropical area of eastern Brazil. And during transient events, the basic state shifts this boundary of westerly winds to the south. So the cloud bands are not allowed to propagate that much into the tropics. So with that, the events would be more transient. They won't last that long and then tend to dissipate faster. during persistent events, this Rossby waves, because of the westerlies are more to the tropics, this Rossby waves can propagate deeper into the tropics and stay longer over eastern Brazil, resulting in more persistent events over there. And this is thinking of the basic state. And then when we analyze the actual event, what we see is that when we have a very persistent event, this event will cause will cause a tendency of vorticity over the region that will feed back the event and sustain it for a little longer. And it can also be thought as a source of Rossby waves on itself. While when we have transient events, the location of this deep convection is a little bit to the south, so more over Southeast and South America. And the advection of vorticity and the vorticity tendency formed by this event is not that strong. So this Rossby, it doesn't form a Rossby wave source as strong as when we have the convection over Southeastern Brazil. So as I mentioned before, we can use this framework also to analyze what happens in climate models. So here I'm going to show an example of a comparison that I'm doing with the atmospheric only climate model from the Brazilian climate model from the National Institute for Space Research on the top. The middle row is the middle and the top row, bottom row, sorry, the models from HADGEM, so from the Met Office, and the coarser resolution N96, and the higher resolution N216. Here I'm showing the historical scenarios, but the results are very similar for the atmospheric only scenarios as well. And well, on the left-hand side, we have a graphic with the climatology or the seasonal cycle of this cloud band. Here I'm looking at all of them together, considering the entire rainy season. And what we see is that all these models, they represent quite well the seasonality, but they tend to delay a little bit the onset of the rainy season. So we tend to have fewer events, especially in November and December, as we are seeing here on the bars, but then we tend to have a little bit too many events on especially on February and March. Among these models that we analyzed, BUM is the one that reproduces a little better the seasonal cycle, but also it's an atmospheric only model. So one of the take homes is that all of these models, they delay the onset of the cloud band season. And they also tend to form, when the cloud bands form, they tend to persist longer. So we have more persistent events, but fewer transient events. And spatially here, what we are seeing is the number of days this event on the map on the left, and the accumulated precipitation during this event on the map on the right. The contours, the red contours are always representing the models, and the blue contours are representing the observation. And the shades are representing the difference between the two of them. So all the models tend to underestimate the number of days over central Brazil and over the Amazon, and overestimated over the South Atlantic conversion zone or over the ocean. And also for Met Office, they overrepresent the number of days. So they put too many cloud bands over the Atlantic Ocean, over the tropical area of the South Atlantic conversion zone. In terms of precipitation, the Brazilian model underestimates the total precipitation over Central South America, while the Met Office models, they overestimate both over Eastern Brazil and also over Southeastern South America. So the models are two-edged over this region during cloud bands, okay? So what are the causes of this bias? So the first thing I'm gonna talk about is the duration of the event. So thinking now about the climatology of the model, I'm gonna use the Brazilian model here as an example, but this is seen in all the other models that I analyzed here. So in upper levels, this is the climatology for zonal winds in upper levels during the rainy season. And what we see, I think the main thing that we see here is this overestimation of the westerlies over extratropical latitudes. So according to the Rossby wave theory, these westerlies are very important to set the environment for this Rossby waves to be able to propagate. So what I'm going to do here is I'm going to analyze how this bias will affect Rossby waves with different wavelengths and zonal numbers. So this map on the right is showing the gradient of absolute vorticity in the shape, and contours, and also the path of a few examples of Rossby waves. So I'm going to focus first on the blue line. So this blue line is only for observation. So I'm just looking at what happens with the Rossby waves using ERA 5 data. The lines marked with squares are Rossby waves with zonal number 2, and those marked with triangle is Rossby waves with zonal number 4. So what we see is that the longer waves, they propagate through extratropical latitudes, while the shorter waves, they propagate through kind of mid latitudes, not so much to the south, but both of them would reach southeastern Brazil. So the circulation will allow for this Rossby wave source over this point over the Pacific to reach the subtropical South America. When we analyze what the climatology will allow for them, for example, we see that the long waves are very similar. So the lines marked with the square, the green lines marked with the square, they kind of follow more or less the same path. But when we see what happens with the shorter waves, so zonal waves number 4, we see that they are deflected to the west coast of South America. So we have this area of reduced gradient of absolute vorticity. So the increase in zonal winds will increase the shear to the north of the jet here, and this will decrease the gradient of vorticity over this region, and this will kind of block the propagation of the shorter waves. We can repeat this exercise for all like different zonal wave numbers and different wave speeds. And what we see here, so thinking about those waves that can reach this latitude over subtropical South America, we see that for observations, again, is the blue dots here, the blue marks. When we get to longer waves, we see much less dots for the other models, as we see for the observation. So in the models, the waves that reach, or they are allowed to reach southeastern South America, they tend to be longer. So these longer waves, they can be related to a little bit longer events if they propagate slower. And also the fact that you have fewer wavelengths reaching this subtropical South America can indicate why we have fewer events, especially in the beginning of the rainy season. Okay, so basically, these anomalies that we are seeing, they are stronger in November and December, and they can be related to the delayed onset of the rainy season or the cloud band season over this area. Then another thing that we can analyze is why we have this wet bias over southeastern Brazil, especially on the HADGEM model. So just to remember the bias that I'm talking about. So this is an example for what happens during November and December. So only during the onset of the rainy season. What we have during these 2 months is a weakening of the zonal winds over subtropical South America. So this is the region where the winds are coming from westerlies to easterlies, and it's the latitude where we have the subtropical jet, especially in synoptic scale. So if we weaken this wind here, if the winds become more easterly over this region, what we do is we increase the shear, or the meridional shear between the extratropics and the tropics. So we have weaker winds over like around 20 degrees south and stronger winds south of 40 degrees. And the shear will increase, and this will also help increase the stationary Rossby wave number, which means that the critical line where your Rossby waves can propagate into, they will be shifted south. So that's what we are seeing in this graphic on the bottom. So with the brown and reddish colors here is for the HADGEM models. So with that, your cloud bands, they cannot reach that much into the tropics, and they kind of like become trapped over subtropical latitudes, so increasing the precipitation over this region. One last thing that I want to show, this will be a little faster, is how all of this is depicted into the convective permitting model. So in this model, instead of having a prescribed convection or a parameterized convection, the convection is actually resolved into in the model, which kind of improves the representation of all the land atmosphere feedbacks and all the way that the presence of the convection will change the circulation environment. So what we want to see with that is to see if these models are able to better represent the cloud band. So what I'm going to show here is kind of like a zoom in into the resolution of the model. So I'm going to start showing the number of days with events, a similar map, contours indicating the number of days and the models and the observation, and the shades indicating the differences between the two of them. And this is AMIP only models. And this is the highest, the coarsest resolution of the models in the Met Office. And we see a bias of about almost 50% less events during the rainy season over certain areas of tropical Brazil, and a bias of about 20 to 25% more events over the subtropics on this scenario. If we move into the resolution, so now we're going to go to a finer resolution one. The bias over central Brazil actually increases in this model. We didn't investigate it yet why, but that's something that we want to check, why we have larger bias in a finer resolution model. This is, sorry, I went backwards. This is the even higher resolution global climate model that is used as a forcing for the convective permitting model. So in these results, we see improvements in the bias over the subtropics, but still a lot of bias over the central area of Brazil. And moving even further, now we see the control run for the convective permitting model. So this is a regional model run with convection fully resolved. And we still see a very large improvement in the number of days with events over central Brazil. We still see a little bias over subtropics, but there's a lot of value gain into using this convective permitting models. And this is just kind of like to wrap up this idea. This is again the climatology, and the shades are the resolution of this model. So the lighter shades are the coarse resolution, and the darker shades are the finer resolution up into the convective permitting, the darkest brown. And what we see is that these models are able to better reproduce the seasonal cycle of the cloud band over South America. We still have a few biases, but they do have a lot of improvement. Switching gears a little bit, this is something that we are developing also, which is to expand this analysis to the entire Southern Hemisphere. So this is kind of like coming full circle with what we discussed, with what I showed in the beginning. So this is just showing where we do have this cloud band events over different parts of the Southern Hemisphere. And this is showing an analysis of thinking of how ENSO events can change the occurrence of cloud bands. So just as an example, what I thought it was really interesting is that during ENSO events or during El Nino events, the South Pacific convergence zone is shifted to the north, especially during the peak of the rainy season, so December, January, and February, while, for example, the South Atlantic convergence zone shifted to the south. So we do tend to have more cloud band events over subtropical South America and fewer over Eastern Brazil. I won't dig too much into details on this one. I just want to show this as a tool that can be used to see how these cloud bands, they occur over the entire Southern Hemisphere and how they can interact with one another. So the idea of using this analysis is to understand how, for example, the South Atlantic convergence zone can be a source of Rosby waves that eventually can cause precipitation over Southern Africa, for example. So this is very incipient. We are starting to work with this. Didn't develop this very much yet, but we do have a website, a different website, where we have like almost a real-time monitoring or near real-time monitoring of this cloud band. So I'm just showing how it was in past May, where we have a lot of events over Eastern Australia. So the cloud bands were forming way to the south and west of what they are used to, or of their climatological location, represented here by the contours. And this is the El Nino influence during this month, where during La Nina, which was this past year, you have an increase on the number of cloud band events over this region. So it's an indication that maybe one of the causes of this excessive precipitation that we saw over Eastern Australia during past May could be forced by La Nina, among other things, of course. So you can check this webpage on the QR code on the right. So as a conclusion, I just want to highlight how the importance of this framework or the importance of use event-based data sets into understanding the circulation patterns leading to different cloud band events, for example, this type of things can be used also to other forcings or other weather systems, and also the usefulness of this into understanding biases in climate models. Also, this could be a very useful tool in seasonal to seasonal prediction. We are starting to implement this in partnership with the National Institute for Space Research. We're starting to implement this into their S2S models to see if this could actually add value to their forecast. Also, in terms of next steps, I think there's a lot to be done here. One of the main things that I want to do is to use machine learning to identify kind of like the weather systems that are behind this cloud band event. So these cloud bands are a mixed bag of a lot of things, and machine learning could be a way to separate different weather systems resulting in this cloud band event. So we want to identify better what's happening over the tropics and how the dynamics of the tropics can also affect the formation of this cloud band. Where is the moisture coming from? And also improve this identification of these events over the southern hemisphere. So thanks again for having me here today. I'm going to leave here the QR code for the both web pages that I showed. So the top one is the one with kind of like a data set of the event. And the bottom one is kind of like this real-time monitoring of the events over the entire southern hemisphere. Well, thanks again.
Thank you, Marcia. That was a great talk. Enjoyed it very much.
Sorry, I feel like I went a little bit too far.
No, not at all. No. I think it was half an hour, and that's perfect. But it was also very clear, and it's very nice. Okay, so anyone watching on YouTube, you can make your questions there, and I'm going to switch to Spanish a little bit. And bueno, a quienes están acá somos pocas. Si quieren hacer alguna pregunta, pueden directamente abrir su micrófono o poner la pregunta en el chat. Y mientras, I'm gonna make a question while you guys think. So when you were showing, I have many questions, but I was just on the last part, when you were showing the response for ENSO events, if I read the maps correctly, you find kind of a non-linear response, right? Because you see in the Pacific, you see, there, like a shift. So more number of events towards the north of the, South Pacific conversion zones, but that was also the response for La Nina, right?
Yeah, so here is El Nino minus La Nina. So
that's
during El Nino, so during El Nino, you have the shift to the north over the Pacific. And during La Nina, you have the shift to the south, kind of like what we are seeing in, we saw this in the fall over the Pacific. And then over South America, the shift is opposite. And I didn't have time to go too much over the graphic here, but what's also interesting is that here we are showing the number of events during El Nino in red and La Nina in blue, so counting all the events. And we have an increase in the total number of events during La Nina in December over South America. But then when you go to January, this kind of shifts. It's the opposite. You have a decrease in the total number of events. This decrease is not that significant as it is in December, but like when you see it spatially, like this map for December and January and February, you also see this reversal over South America.
And do you have any idea of why that is?
I'm not a very El Nino person, but I know that like in general, El Nino increases, or La Nina increases the support for the development of convection over tropical regions in Brazil, while El Nino will change like the Walker circulation over the subtropics, especially and focus the precipitation over the subtropics. I don't know exactly the mechanisms, and this is something that we would like to kind of try to understand to see kind of this connection with the cloud bands over other areas. But it's similar to the mechanisms that we see described when we talk about precipitation over South America during El Nino and La Nina. So the cloud bands, they are responsible for most of the precipitation during the summer. So usually what you see in the climatology or in the kind of like when you do composites of the total precipitation, it's more or less similar to what you see when you composite only those days with cloud bands.
Thank you. Yeah. Is there any other question? I'm tempted to make some other questions, but I won't. I don't want to take over all the time for questions myself. Okay, so I have another question regarding the adaptation of your algorithm for South America. So what were the main differences, or what did that adaptation require? Or
I think, let me show again the slide
because
here.
perhaps you said it, but I missed it.
No, I actually didn't explain too much because so many details sometimes. So I think this in this graphic, this map on the right is a little bit clearer. So if you look at where the cloud bands are forming over South America compared to kind of like more or less the latitude that it's forming compared to where it's occurring over Southern Africa, they occur at a different latitude. So they start further north, they finish further south. Here I just cut out areas of too deep convection to avoid a lot of noise from areas where you always have convection. So the cloud bands, they tend to be a little longer. So this is one thing that we needed to adapt to see how into what geographical area the cloud bands were forming. And I think most importantly is the OLR threshold to identify. So we are using, for the observations, we are using a threshold of 225 watts per square meter. And that's a little bit lower than what was done for Southern Africa. So usually the cloud bands over South America, they are more intense. The convection is deeper, so the OLR is lower than over other areas. And that's the difficulty that we have, for example, to identify the cloud bands over Australia, where they are not that strong. So the OLR is a little bit higher. We compare, to come to this number of 225 watts per square meter over South America, we compared the events with the occurrence of South Atlantic convergence zones. So we have a database of observed South Atlantic convergence zones over Brazil. And this was the OLR, the threshold that best reproduced this observed data set. Of course, we have much more events identified than just South Atlantic convergence zones. So we have much more days with cloud bands than days with observed South Atlantic convergence zones.
Cool. There was much more to that question than I had in mind. That's very interesting. So Nadia has another question. She says, I'm not sure if you mentioned this, but have you observed any long-term changes in South American cloud bands?
Thank you for this question, Nadia. I did observe. I am trying to think if I can have this in the presentation quite quickly here, because I did have this result somewhere else. Just a second. So I'm going to show some results using the hemispheric or the Southern Hemisphere event. But yeah, we can have an idea with that. So this is the changes that we see between these two periods on the top. So I'm looking at the beginning kind of like the end of the 20th century from 79 to 2001. And the difference between this period and the more recent years between 2003 and 2019. This is kind of like a weird, weird period because I removed all ENSO years that are listed here on the bottom. Because if you keep the ENSO years, this type of kind of like decadal changes or changes throughout the time frame that we are checking, they will be a little bit different. So discounting the effects of ENSO years, we do see kind of like this reduction in the number of events or days with events over South America. And when we check throughout the month, this is for December, January, and February. And what else do I have here? Sorry, this was for another presentation, so I didn't highlight South America. But usually what we see is kind of like this decrease in the number of days, especially in the beginning of the rainy season. So the impression is that the onset of the cloud band seasons are starting to be delayed in October and November. And we do see a little bit of increase over the ocean, but it's not very significant. In terms of total precipitation, I don't think I have a slide here. No, I don't think I have a slide there's a slide for South America. So this is number of days in November on the left, and then December on the right. You start seeing kind of like this delay of the rainy season. I don't think I have a slide for precipitation in this case. So I hope I answer your question.
Yes, thank you very much.
Great.
Okay, we have a comment on YouTube. Thank you so much for this talk. It was a very interesting topic, particularly for the potential of cloud band identification in S2S prediction for northern Argentina. That's a comment from Sabrina Ayala. Thank you, Sabrina. So I don't know if you want to answer to that comment.
We are starting to work with S2S. As I mentioned, we have partners in the National Institute of Space Research, and there's a master's student there trying to see how we can use this framework on an S2S environment. So the idea is kind of like, since S2S will work differently from like a global climate model where you have different ensemble runs with different starting dates, we are starting to develop a framework to implement this cloud band events idea identification into the S2S. So we want to see if that could be used as a tool in the future. So the first step is to see how we can implement this into this S2S space, I want to say, and then see if by identifying this cloud band with a certain like 1 week or 2 weeks of antecedents or anticipation, we can improve forecast in this case would be for Eastern Brazil. So especially over the areas where you do have a lot of precipitation coming from this cloud band. But I believe that could be also the case for if we focus over southeastern Brazil or southeastern South America, North Argentina, as she said. So I think it could be used.
Cool. Okay, so we're reaching the hour, and this was a great seminar. I think this is, just so you know, this is the first seminar of this semester, so people, I guess, are getting used to this new time and day. So we were doing them on Thursdays. That's also, but as we were saying before, a lot of people watch this in YouTube and think we'll find it very interesting. Yeah. Sabrina says thank you for that answer.
Yeah, so anyone that wants, if you watch it on YouTube later and you have any questions, you can just email me. There's my email on the last slide. So yeah, feel free to reach me and I'll be happy to answer any questions.
Thank you, Marcia.
Well, thanks again for the opportunity.